We physicists have held up 100 years, beginning around 1916, for this photograph. It is a nearby black hole that might just be one of the most captivating and perplexing quirks known to man. They are immense beasts in terms of power and simultaneously, in every way that really matters, vague to us. A black hole weighing perhaps 2 to multiple times the mass of the Sun, anyway, taking into account the investigation that was placed into them over the last 20 or 30 years, we've gone from knowing almost nothing about them to getting to figure out progressively more about them. Things have as of late gotten more crazy. Ms. Kaku recently revealed that we at long last got a look at what's inside a black hole. And this new information sheds light on the nuances the universe of science might have missed from the very beginning. Go along with us as we dive deeper into black holes and uncover what's inside. Space is gigantic, but what are black holes? Before we get into the details of what Ms. Kaku found, we need to examine the basics. Although most of us have some idea of what black holes are, there are still a few gaps in the right information. You see, in 1916, Albert Einstein published his theory of general relativity, which predicted the existence of black holes. At that time, the concept of black holes was entirely theoretical. It required 50 more years for scientists to find proof that black holes truly exist. This happened during the 1960s when they were studying the Sine X1 grand body and observed a peculiarly brilliant blue star that was emitting X-rays. This star was definitely not an old object but was evading a monster black something. Upon further assessment, it was seen that the X-rays weren't moving around on their own. They were being sucked into the black object they were orbiting. Thus the name black hole. This discovery was huge because it provided evidence that black holes truly exist, and they weren't a product of Albert Einstein's wild imagination. While that was incredible, it also meant that there was this astonishing phenomenon in space that we desperately needed to learn more about. So, scientists from one side of the planet to the next got to work. This black hole was named Cygnus X1, and it is located in the constellation Cygnus, about 6,000 light-years from Earth. It was no small discovery. It's several times brighter than the Sun and incredibly dense, which gives it a strong gravitational pull. The gravitational pull is so strong that not even light can escape it. This is why it is known as a black hole. The concept of a black hole is both fascinating and terrifying. It is a region of space where gravity is so strong that nothing, not even light, can escape. Anything that gets too close to a black hole will be pulled into it, gone forever. However, that element of danger makes it all the more essential to learn everything there is to know about them. Was this it, or were we just beginning? The answer turned out to be the latter. After the discovery of Cygnus X1, scientists began searching for other black holes. They found that there may be almost 100 million black holes in the Milky Way alone, but because they are so incredibly difficult to detect, we still don't have an exact number. Apparently, there are a few million black holes in the Milky Way, which makes them even more important to study. So let's break it down. The main issue with black holes is always going to be gravity. Their gravitational force is so intense that anything that enters it gets crushed down immensely until it becomes a singularity. In simpler terms, black holes are like gigantic vacuum cleaners that suck everything in. One of the most frightening parts of the study of black holes is the fact that if someone were to fall into one, they would eventually become a single line. This process would happen slowly, and the person would die before the actual breakdown of reality sets in. So let's just say that no one should step into one, but they are everywhere. So could we be in danger? Even though the closest black hole to Earth is around 500 light-years away, it's still close enough to raise concerns. In 2021, scientists were able to create the first clear photograph of a black hole, the M87 black hole. This black hole was captured over several nights, and with every photo, the researchers gathered more evidence about it. They had to arrange the individual photographs to fill in the gaps. In doing so, they were able to discover that there are 3 layers to a black hole. It's not just one single growing hole of nothingness, as many people believe. Things are much more complicated than that. To even get to the nothingness of a black hole, you have to survive the first 2 layers. The first layer is known as the event horizon. Once you pass the event horizon, pushing forward is your only real option, and you will be sucked into the black hole. The 3 layers degrade from there. The second layer is the photon sphere, where light orbits the black hole. Any light that enters this region will be captured and cannot escape due to the black hole's gravitational pull. Finally, we come to the third layer, the singularity. This is where everything that enters the black hole is compressed down astronomically until it becomes a singularity. The singularity is a point in spacetime where the laws of physics as we know them break down, and we can't predict what happens next. Now, what complicates everything is that each black hole you study will be completely different from the last. Sure, they generally follow the same three-layer structure, but the way they function could be vastly different. Right now, if this were anything else, we would just jump back to those telescopes and focus on the basics in detail. But with black holes, you can't really do that. Scientists can study black holes indirectly by observing the radiation they emit and the gas and dust that surrounds them. Sending a probe into a black hole is impossible because anything that enters the event horizon is pulled toward the singularity, where it is compacted into an imperceptible state. The study of black holes is an ongoing journey into the unknown. As more data is gathered, scientists are able to refine their models and improve their understanding of these cosmic phenomena. However, the most significant challenges remain: the difficulty of directly observing black holes and the mysteries that still surround their true nature. For instance, while we know that they emit powerful radiation, we still don't fully understand how this radiation is generated, or how the matter that falls into black holes is processed. Despite the limitations, advancements in technology like the Event Horizon Telescope have allowed for groundbreaking discoveries like the first direct image of a black hole. This has revolutionized the field and provided a visual confirmation of theoretical predictions made over a century ago. Yet, even with all the progress made, questions remain. Are there other, even larger black holes lurking in the distant reaches of space? Can black holes merge to form even more massive supermassive black holes, as some scientists hypothesize? And, most intriguingly, can we ever uncover the true nature of the singularity at the center of a black hole, where the fabric of spacetime breaks down and our understanding of physics as we know it ceases to apply? For now, all we can do is continue observing, theorizing, and hoping that future generations of physicists will uncover the answers that have eluded us for so long. The study of black holes is far from over, and with each discovery, we inch closer to understanding some of the universe's deepest mysteries. In the meantime, black holes remain as enigmatic and fascinating as ever, not just as regions of space, but as windows into the very fabric of spacetime itself. Little points, so you can't precisely squander billions of dollars just to get an impression each time. In light of the fact that the second the test draws near enough, it will brown nose. Brown nose L will be squashed into nothingness as a result of that unmistakable issue. Scientists are left with no choice except for to concentrate on these items in a two-layered manner, despite the fact that they are three-layered singularities in the doubt. To make matters significantly more challenging, there are also the two issues of every dark hole being unique and the laws of physics as we probably know them, breaking down when we attempt to examine the inside of dark holes. Traditional methods of scientific inquiry don't actually apply to the study of dark holes. That doesn't mean scientists haven't been busy. There are lots of different theories and explanations for dark holes, and with every one, things get increasingly fascinating. Perhaps one of the most compelling theories about the formation of dark holes is that they are created from collapsed stars. By then, when a star drains its fuel, it can no longer produce sufficient energy to balance the force of gravity that is continually pulling inward. So, the star begins to collapse on itself, contracting and becoming denser as it does. If the star is massive enough, this process can go on until it transforms into a singularity. To understand the nature of dark holes more deeply, NASA scientists directed their focus toward the center of the universe, M87. Astronomers noticed a truly powerful whirlpool of extremely hot hydrogen gas that was revolving at a stunning speed of 1.2 million meters per hour. The sheer force of the spinning gas disk should have made it violently fly apart in every direction. However, it didn't. Scientists found that there must be a massive mass gathered at the center of the system to prevent this from happening. This enormous object weighed as much as 2 to 3 billion suns, and it had to be a dark hole. But that doesn't seem to be the only theory regarding dark holes. In 1963, New Zealand mathematician Roy Kerr used Einstein's equations of gravity to give the best description of a spinning dark hole. He showed that a spinning dark hole wouldn't collapse into a point, as previously thought, but rather into a ring of fire or a thin disk. The disk would spin so rapidly that outward forces would prevent it from collapsing. This alternating disk of matter is known as the ergosphere, and it's the region surrounding the dark hole where the laws of physics begin to break down. However, the most intriguing feature of Kerr's solution was that it predicted the existence of an Einstein-Rosen bridge, also known as a wormhole. This is a theoretical passage through spacetime that connects two separate regions of the universe or even two parallel universes. The idea is that if one were to fall into a dark hole instead of being crushed to oblivion, they would be sucked down a passage through the ring of fire and shot out a white hole into a parallel universe. To understand how this works, we need to look at the concept of spacetime in Einstein's theory. The reality we experience isn't made up of independent entities but is interconnected, forming a four-dimensional fabric known as spacetime. Objects with mass bend this fabric, creating a gravitational field that makes other objects move toward them. Now, imagine a piece of paper representing spacetime. If you place 2 points on the paper and draw a line between them, this is a depiction of how objects travel through spacetime. But what if you could fold the paper in half and create a shortcut between the 2 points? This is the basic idea behind a wormhole. A shortcut through spacetime that connects two distant points in an instant. Wormholes aren't just a sci-fi concept. They are actually a prediction of general relativity. Although no one has ever observed one directly, the reason is that wormholes are inherently unstable and would collapse quickly. However, the existence of an Einstein-Rosen bridge would mean that dark holes are not only massive vacuum cleaners, but they could also be gateways to different regions of spacetime. So, could we use a wormhole to travel through existence? Unfortunately, the answer is probably no, not yet. Even if we could stabilize a wormhole, it's unlikely that we would be able to use it to travel faster than light. Einstein's theory of special relativity predicts that the speed of light is a hard limit on how fast anything can travel through spacetime. Still, the theory of wormholes and dark holes as pathways to different parts of the universe, or even to different times, has been a subject of interest and speculation among physicists for years. The possibility that there might be shortcuts through the fabric of spacetime, allowing travel across vast distances or even into the past, could be revolutionary if we could ever achieve it. One of the most fascinating ideas in this field of study is the CR wormhole, named after the mathematician Roy Kerr, who first described Einstein's equations of gravity. This type of wormhole is essentially a hypothetical tunnel through spacetime that could connect two distant points, such as two different universes or even two different times within the same universe. The Mutt wormhole is ring-shaped, like the mirror in the story of Alice in Wonderland, and could potentially move a traveler to another universe or another time, where the laws of physics may be very different from what we know. Yet at the destination that could be ordinary. While the possibility of wormholes for interstellar travel or time travel is certainly exciting, as we've mentioned before, it's also a subject of debate and discussion among physicists. Some have pointed out that wormholes, and particularly the so-called K9 wormholes, might be unstable or difficult to traverse due to the extreme radiation and subatomic forces surrounding their entrances. Critics argue that Einstein's equations of gravity, which are used to describe wormholes and dark holes, only apply to gravity, not the quantum forces that govern radiation and subatomic particles. To understand the true nature of these phenomena, a new theory is needed that can unite the laws of gravity with the quantum theory of radiation throughout the universe. This is known as a theory of everything, a single theory that can unify both Einstein's theory of gravity and the quantum theory. Michio Kaku, a famous theoretical physicist, has been working on a theory of everything for many years. While there are many versions of what this might be, the one that has shown promise is the superstring theory. Superstring theory combines gravity with the theory of radiation. The theory proposes that subatomic particles are actually tiny vibrating strings, and that the universe is a collection of these strings. Just as different musical notes correspond to different vibrations of a violin string, different particles in nature correspond to different vibrations of a superstring. An interesting aspect of superstring theory is that as a string travels through time, it bends the fabric of space around it, creating dark holes, wormholes, and other fascinating solutions to Einstein's equations. This means that superstring theory not only unites Einstein's theory of gravity with quantum theory, but it also explains many of the mysterious phenomena we observe in the universe. However, there's a catch. The extra dimensions of spacetime that superstring theory requires are so small that we can't even observe them directly.